0.5%. Now, I know that might sound like a tiny, almost insignificant fraction, but let me tell you, right now in 2024, that is the massive chunk of total global electricity being absolutely swallowed up by classical data centers. Fueled by the booming, relentless demands of AI models, that number is actually projected by the International Energy Agency to more than double by 2030. We are quite literally watching our own technological progress eat into the world's power supply.
And if we zoom in a bit, the localized crisis is honestly even more alarming. Take Ireland, for example. Over there, data centers now eat up over 20% of the country's entire electrical power grid. 20%. It's gotten so extreme that real limits are being placed on building future data centers near Dublin. So, this isn't some distant, far-off future problem. This is a massive energy drain happening right now, right in our backyards. Today, we're diving into a genuinely fascinating piece of research from Physics Today that tackles an incredibly urgent question. As classical computing pushes our power grids to their absolute breaking points, scientists are looking to the next big horizon, quantum computing. But there is a massive, looming giant in the room. Will quantum computing actually save our power grids by solving complex problems instantly? Or will its own unique, demanding requirements completely crush whatever energy reserves we have left? Okay, let's dive into this, the current data center crisis. To really understand why scientists are actively sweating over the energy demands of future quantum computers, we kind of have to look at the brick wall our current classical computing is hitting. The pushback against classical computing's energy drain, it's already happening. 14 different states in the US have introduced legislation to literally ban the construction of new data centers in recent years. Communities and governments are waking up to the hard fact that we simply cannot afford to keep scaling our technology if it requires this much raw traditional power. This immediate crisis is exactly what sets the stage for our next massive technological leap, and it's exactly why researchers are so desperate to get the energy math right this time around. Yes, quantum computers are insanely fast, but let's talk about the quantum noise problem.
And this brilliantly illustrates the core issue. The natural pivot for everyone is toward quantum computing. And sure, quantum computers are theorized to be exponentially faster, tackling specific problems in a matter of hours that would literally take classical supercomputers many years. But they also come with a fundamental flaw. They are incredibly, almost impossibly, fragile. Classical bits scale linearly and represent just a 0 or a 1. They're incredibly reliable. Qubits, on the other hand, can represent a 0, a 1, or a superposition of both. Adding more qubits increases the system's power exponentially. It's a jaw-dropping amount of raw potential. Because of this, it's super tempting to assume quantum computers will just inherently be more energy efficient. But they severely lag behind classical computers in one critical area, reliability. They are incredibly noisy.
To really grasp why this noise requires so much raw power to fix, you need to understand a little thing called decoherence. Because quantum computers use delicate quantum states to hold information, even the tiniest, most microscopic disturbances in the physical environment will destroy that information. Today's quantum computers have error rates many orders of magnitude higher than classical processors. They aren't fault-tolerant yet. They're what scientists refer to as noisy intermediate scale. And fighting that noise? Well, that is exactly what consumes so much power.
For instance, let's take a look at superconducting qubits. To keep them at their least noisy, they require extreme cryogenic cooling, bringing them way down to between 10 and 35 millikelvin. To put that into perspective for you, that is 2 orders of magnitude colder than the vacuum of outer space. It's even colder than the magnets in CERN's Large Hadron Collider. Just maintaining that extreme freezing temperature accounted for about 80% of the power consumption in one recent study of a noisy intermediate-scale quantum computer. The energy required simply to maintain a usable state is staggering. Let's move to and see how this builds in our next section, calculating the energy cost.
Given how early we are with this tech, pinning down exact numbers is kind of tough, right? But researchers are already doing the real-world math and making some highly educated projections. Quantum engineer Olivier Ezrati recently ran some projections on the future base power of leading quantum computers, assuming we scale them up to 4,000 logical qubits. His findings? Well, they showed power ranging from under 1 megawatt on the low end to over 100 megawatts on the high end. What's absolutely vital to take away from this is that most of these future quantum machines landed right in the exact same power range as today's top supercomputers. Let's anchor this in a specific human terms example so we can really wrap our heads around it. Edward Parker, a physicist at the RAND think tank, calculated what it would take for a hypothetical superconducting quantum computer with 20 million noisy qubits to crack an RSA 2048 encryption key. The electricity demand? 890 megawatt hours. That is the equivalent of powering 85 US households for an entire year, costing roughly $64,000 in electricity for that single, solitary task alone. As Parker concluded, this massive power drain actually means it would be incredibly difficult for a bad actor to afford or even secretly run one of these machines anytime soon.
But looking forward, the broader implications are pretty heavy. A recent analysis by energy scientists at Oak Ridge National Laboratory projected that by the 2040s, if we integrate fault-tolerant quantum computers into today's classical computing data centers, the system-level power demand could easily match the colossal footprint of today's entire data center network. Think about that. If we don't solve the quantum energy problem now, we are just trading one grid-crushing technology for another.
So, we are in a race against time, designing for energy efficiency.
Researchers are well aware of this impending cliff, and they are proactively fighting the issue right now before the technology stales up and locks us all in. Enter the Quantum Energy Initiative. Started back in 2022, this is a volunteer-run global community of over 700 scientists, researchers, and industry professionals. Their entire mission? To support energy-efficient design today. There's even an IEEE working group actively developing standards to define energy efficiency metrics for the sector. The goal is that one day we can accurately benchmark different quantum computers against each other based purely on their power consumption.
Now, what's really interesting about this is how completely counterintuitive the physics can be when you actually start optimizing for energy. A 2023 paper demonstrated a fascinating method. They found that in some instances, if you slightly raise the temperature of the superconducting qubits, which saves massive amounts of cooling energy, but you add more quantum error correction processes to handle the resulting noise, you actually end up with a larger, yet overall more energy-efficient computer. Adding more computational process literally saved physical energy. It's wild.
And hey, these aren't just theoretical concepts drawn out on a chalkboard somewhere. They are actually working. The French government recently granted 4.5 million euros to quantum companies to study this exact efficiency. Using these new metrics, the company Quandela identified an energy-efficient regime for its photonic quantum computer. They successfully solved an algorithm way more energy efficiently than a classical computer could, even though the quantum machine actually took a longer runtime. It proves that with intentional, smart design, energy-efficient quantum computing is absolutely possible.
Let's step back and look at the paradox of progress. Let's step back from the raw physics for just a second and look at the broader sociological and philosophical implications of scaling up this technology. Because getting the machines to run efficiently, that's really only half the battle. Researchers are incredibly anxious about falling victim to the Collingridge dilemma. It's basically this idea that the harmful consequences of a new technology are very hard to understand when it's just starting out, exactly like quantum is today. But by the time those consequences become glaringly clear, the technology has already matured and integrated itself into society, making it extremely difficult to control or regulate. Scientists are terrified of repeating the exact same energy mistakes we just made with the classical AI boom.
This intense sense of urgency is perfectly captured by researcher Ziki Sesker, who reminded the entire community. Technology and innovation are not science. Although we might be scientists, we need to be aware that the consequences are different. The pure science of quantum computing is beautiful, no doubt about it. But the very moment it becomes an applied technology, drawing real power from a shared grid, it carries an urgent, real-world responsibility for all of us.
So what does this all mean? It brings us to this final provocative thought: the rebound effect. Let's say these incredible scientists succeed. They beat the noise, they figure out the cooling, and they make commercially relevant quantum computing beautifully energy efficient. Will that actually save our power grid? Or, by lowering the costs and energy requirements, will companies simply buy exponentially more computers and computing time, ultimately draining the grid anyway? Are we building a vastly more efficient engine only to drive it 1,000,000 times further? That, my friends, is the ultimate quantum paradox we have to solve.